This is just a review of things that'll come up when we start this next section. So this is just a review. These things you should have seen in Abstract 1, but just to remind you, there's a definition. Suppose let G be a group. And H be a normal subgroup of G. Then there's a map you can define between G and G mod H. In fact, it's a map you've used in one of your homework problems in showing G was isomorphic to G mod 1. So I'm just defining that same map. I'll call it phi from G to G mod H by and of course we'll take every element of G to its left coset. Phi of little g is GH, and we'll do that for every G in G. Okay? Phi is called the natural map. And in your next homework, there'll be some problems involving this natural map. Why am I telling you about this? Because it's going to come up in the next section. And we'll need the natural map. Another review thing, but you should have seen it, but if not, now you're seeing it now, and you'll have some problem about it so that you get used to it. Why is it called the natural map? Because it's pretty natural. Send every element to its left coset. Where else would you send it to? If you want to make a map from a group to a quotient of that group. Another definition. Again, this is something you've probably seen before, but again, it's going to come up. Definition. Let G1 and also G2 be groups. Phi going from G1 to G2 be a homomorphism. H be a subgroup of G1, and say K be a subgroup of G2. Then you can define several things. Okay, so these are just definitions. Then thing 1. It's called the image of H. You can take phi of every element in H, put those answers in a bag, and you get a bag of elements in the group G2. That's called the image of H. The symbol for it is, of course, phi of H. So that's equal to the set of all phi of little h's, such that H is in H. And it's called the image of H. Thing 2. You can do the same type of thing with K, even though you can't apply phi to K, because K lives in G2, as you can see right here. Follow the pen. But you can take what's called a pre-image of K. Now the symbol for that is phi with a -1 on top of K. Doesn't mean phi inverse. Phi may not have an inverse. No one said phi was 1-to-1. What does it mean, though? It means what we're about to say right now. It's equal to the set of little g in G, such that phi of that little g ends up landing in K. And it is called the pre-image of K. In words, it's called the pre-image of K. And finally, I think that's it, okay, for this definition. Now, there'll be homework problems on these things. Why, again, am I telling you this? Because it's going to come up, and we're going to want to remember these things. So the homework problems about these things, and the next thing I'm going to mention, will help you remember it and also work with it. But again, these are old ideas from Abstract 1. Finally, the last review thing before we start the next section is the first isomorphism theorem, as we will use this repetitively to do what we have to do in the next section. So let's write it down here. Keep adjusting these things, of course. Okay, this is the last review thing. It's a theorem from Abstract 1. Should remember how to prove this theorem. But anyway, it's called the first isomorphism theorem. And it goes like this. Let G1 and also G2 be groups, and phi going from G1 to G2 be a homomorphism. That's all you need is two groups and a homomorphism. Can't ask for less than that. Then instantly we can say two groups are isomorphic. Which two? A quotient of the first group is isomorphic to its image that lives in the second group. In other words, then G1 mod the kernel of phi is isomorphic to the image of G1. With that being said, that's it for the review. There'll be homework problems on these things, just to not make sure you're just writing these symbols, but really know it. Okay, and are ready to whip it out and use it as weapons to do a problem. Okay, so now we're going to start the next section. Again, making lots of adjustments each time. Lots of fun adjustments that are always a blast. Wow, get that off of there. Okay, so the next section in the book is called 4.6. And it's called Sylows theorem. Ludwig Sylow was a Norwegian and mathematician, and he discovered something very interesting about group theory that applied to any finite group. It was so interesting that it changed group theory forever. You literally cannot do group theory without Sylows theorem. If you pick up a journal paper, you'll see it plastered all throughout the paper, used whenever the guy wants to pull it out as a weapon. Okay, but first we'll start with a definition. Let's see. Okay, definition here. Let G be a group. H be a subgroup of G. P be a prime. And N, not and, but just N be a positive integer or possibly 0. And suppose p to the n divides the order of g, but p to the n plus 1 does not divide the order of g. Okay? So if you look at this prime, this number, p to the n, p is prime, but p to the n isn't, of course. But if you look at this number, p to the n, you can see right here, follow the pen. It divides the order of g, but the very next power of p doesn't. So p to the n is the highest power of p that divides the order of g. That's kind of a special number, but it's a lot to say. So let's attach a symbol to it. Okay? And so about this number, we can make the following definitions. Then, one, we call this number p to the n, the highest power p that divides the order of g, the pth part of g. And we attach this symbol to it. It's the order of g with a subscript p. And it is just a symbol to stand for that number, p to the n. And in words, it's called the pth part of g. Okay? So it's just a number. What happens if a subgroup, follow the pen, like this H, happen to have the pth part of G as its order? That would be interesting. Well, if it does, then that subgroup H is called a Sylows P subgroup, named after the guy who discovered these things, Ludwig Sylows. And that's definition 2. H is a Sylows P and then a hyphen subgroup if the order of H is that pth part of G, p to the n. Now, you might wonder if a group has a subgroup like this. I mean, maybe it doesn't. You never know. Maybe no subgroup of a group would have the order being the pth part of the group for a given prime p. But, not knowing that there are any of these subgroups, we could still, if there are, collect them and put them in a bag. Put them into a nice big set. But that set would have to have a name. So let's invent some notation for it. And that will be definition 3. The first 3 letters, follow the pen, of Sylows' name are used in the notation for this set. So the set of Sylows P subgroups is denoted by SYL and then a sub P of G. And so that is just the set of Sylows P subgroups of G. So let's write it mathematically now in set builder notation. So that would be equal to the set of H such that H is a Sylows P subgroup of G. Put a little period there. And that is the definitions. Okay? Now, of course, we're going to be acting on this set. You can bet your bottom dollar. Okay? In various ways. Okay, so let's look at an example. A real live group, a real live prime, and a real live Sylows P subgroup. Make a few adjustments. Yeehaw. How about let's look at a group you know, S3. If you look at the order of S3, it's equal to 3 factorial. That's 3 times 2. And if you look, I've left it prime factored. because we're interested in Sylow P subgroups, where P is a prime. Okay? So, if you look at the highest power of 2 that divides the order of S3, you can see right here it's 2. 2 squared won't divide 6, but 2 does. So you could say, so the 2th part of S3 is 2. And if you look right here where the pen is, you can see the highest power of 3 that would divide the order of S3 is just 3. And so you can say, using the notation above, right here, the 3rd part of S3 is 3. So that means if we could find a subgroup of S3 that has order 2, then by this definition, right here, follow the pen, it would be a Sylow 2 subgroup of G. Well, it's easy to find a subgroup of S3 of order 2. Just take an element of order 2 and look at the cyclic subgroup generated by that element. It would just have 2 elements. And an element of order 2, there's several, but one is the 2 cycle, 1, 2. So you could say, now, if you look at the cyclic subgroup generated by 1, 2, that would consist of the powers of 1, 2. So there's 1, 2 to the first, and 1, 2 to the 0, that's the identity. Then 1, 2 to the first, that's 1, 2, and 1, 2 squared is the identity again. So there is all the powers of 1, 2. We know from abstract 1 that's a subgroup of S3. And its order is the number of elements it has, follow the pen, 1, 2, is 2, which is exactly the 2th part of S3. Thus, we have found ourselves the Sylow 2 subgroup of S3. Thus, the cyclic subgroup generated by 1, 2 is a Sylow 2 subgroup of S3. So it's in that set of Sylow 2 subgroups. It's an element of it. As this is a set, follow the pen, this is a set of subgroups. Why? Because it says it right there in definition 3. Follow that pen. See that? It says it right there. Okay? Likewise, I can find 2 other Sylow 2 subgroups of S3. Just take the other 2 cycles. They each generate a Sylow 2 subgroup of S3. So let's do that. Likewise, the cyclic subgroup generated by 2, 3 is a Sylow 2 subgroup of S3. And the cyclic subgroup generated by 1, 3 is a Sylow 2 subgroup of S3. Let's look at another group. Make all those fine adjustments. Another example. Let's look at A4. The order of A4 is just half the order of S4. So it's 4 factorial over 2. But if you don't know why the order of AN is half the order of SN for every n, don't worry. You're going to prove it for me in the next homework using an action and not any other way. Okay, so anyway, that would be 4 factorial is 4 times 3 times 2 times 1 over 2, and that's all 12 as these 2's cancel. And now I'm going to prime factor that number. It's 2 squared 3. So you could see the highest, follow the pen, the highest power of 2 dividing the order of A4 is 2 squared. So I could say, so the 2th part of A4 is 2 squared, or 4. And you can see, follow the pen, the highest power of 3 that would divide the order of A4 is just 3. And so the 3rd part of A4 is 3. So let's use our notation now. The 3rd part of A4 is 3. So that means if I can find a subgroup of A4 that has 4 elements, then I found myself a Sylows 2 subgroup of A4. Now if we run into a subgroup of A4 that did have 4 elements right before we left for spring break, I'll remind you of him. I'll call it H. Let H equal the identity and all possible 2-2 cycles. 1, 2, 3, 4. 1, 4, 3, 2. 1, 3, 2, 4. Then we saw before spring break that each one of these elements here in this subgroup H is its own inverse. And so there's inverses in here. Finally, we saw that the product of any 2 of these is the 3rd one, not including the identity. The product of any 2 of these, like in other words, this one times this one is this one. Compose them and see for yourself, baby. And this one, follow the pen, times this one is this one. And this one, woo, times this one is the middle one. So it's closed. And so it's a subgroup of A4, and you can see it's composed of just even permutations. You can see it has order 4. Let's say that. Let's say that. Also, the order of H is 4, which is the 2th part of A4. And so, H is a Sylows 2 subgroup of A4. And we found one. What about 3 over here? Follow the pen. What about 3? I wonder if A4 has a Sylows 3 subgroup. Let's see. For that, we'd have to follow the pen. The 3rd part of A4 is 3. So we'd have to find a subgroup of A4 of order 3. Then we found a Sylows 3 subgroup of A4. Well, that's easy. Just take an element of order 3, if A4 has one, and look at the cyclic subgroup generated by it. That would generate a subgroup of order 3. Well, sure, A4 does have elements of order 3. In fact, it has 8 of them. Just any of the 8 3 cycles. Okay, so let's take 1, 2, 3. How about that? Now, the cyclic subgroup generated by 1, 2, 3 consists of, better make an adjustment here. Okay, so I started writing now. The cyclic subgroup generated by 1, 2, 3 consists of the powers of 1, 2, 3. So there's 1, 2, 3 to the 0. There's 1, 2, 3 to the 1st. And 1, 2, 3 squared, compose it with itself, baby. That's 1, 3, 2. See for yourself. And we know that's a subgroup of A4 because these are all even. Let's put a little period there. Also, contraption's ridiculous. Also, the order of the cyclic subgroup generated by 1, 2, 3, count for yourself, 1, 2, 3, has order 3, which is the 3rd part of A4. Yeah, right up here, follow the pen. Right up there, that's the 3rd part of A4. Let's put a little period there. Thus, the cyclic subgroup generated by 1, 2, 3 is a Sylows 3 subgroup of A4. Well, let's see. So far it seems like these groups always have Sylow P subgroups. Let's go back up to the top and look at the order of A4. Follow the pen. Here's the order of A4. We found a Sylow 2 subgroup, and we found this H right here. And we found a Sylow 3 subgroup, the cyclic subgroup generated by 1, 2, 3. Okay, follow the pen. And in S3 we found Sylow subgroups. Let's take a prime that is not in the order of A4 and see if A4 would have a Sylow P subgroup for that prime. How about 5? So you don't see a 5 here, right? Okay? So let's examine the 5th part of A4. Oh, better make an adjustment. Better make these adjustments, baby. Gotta keep adjusting. Okay? So I'll just say, finally, if we look at the 5th part of A4, the notation just means it's that. That's just a symbol that we agreed to call it a page ago. That would be the highest power of 5 that divides the order of A4. Follow the pen. The highest power of 5 that divides this number, what's that? Man, 5 doesn't even divide that. But there is a power of 5 that divides this number. It's 5 to the 0, or 1. Okay? Follow the pen. So that means the 5th part of A4 is 5 to the 0, or 1. So that means if I can find a subgroup of A4, hopefully I didn't say A5, okay? A4. If I can find a subgroup of A4 that has order 1, then I found a Sylow 5 subgroup of A4. It's easy to find a subgroup of any group of order 1, just the identity. So let's say that. Also, just the identity subgroup has order 1, which is the 5th part of A4. Put a period. Don't want to tell you too much at once. Better put a period. Thus, the identity is a Sylow 5 subgroup of A4. Let's generalize that incredible discovery. Similarly, the identity is a Sylow 11 subgroup of A4, since the 11th part of A4 is 11 to the 0, or 1. So it does seem like these groups always have a Sylow P subgroup, like every time. I wonder if you took any group and any prime, would that group have a Sylow P subgroup for that prime? Yeah, that's what Ludwig Sylow wondered. And amazingly, he was able to not just say it does, but prove it. And that will be done in our next lecture. Today I'll be sending you a homework, and it will involve some of the review things, some, of course, everything involving actions, mostly, and then also some stuff about our lecture today. But yeah, in our next lecture we'll be out to prove what Ludwig Sylow proved in the late 1800s, is that every group for every prime P always has a Sylow P subgroup. Have fun, stay safe, and enjoy your group theory.